So we started today looking at our definitions, making sure that we understood what acids, bases, that sort of thing were. This is a bit of an overview of acids and bases and how they are basically opposites of each other. So we met the acids, we just learned that acids can give away an H+, which we're going to call a proton in this chapter. We've learned that bases will accept that hydrogen. And in doing so, when an acid and a base meet, it's called neutralization. We measure how acidic or how basic something is on a thing called the pH scale, which I've put across the top. There is a 0 value, so 0, 1, 2, 3, 4, 5, and 6. If it's any of those numbers, it means it's an acid. If it's above 7, so 8, 9, 10, 11, 12, 13, 14, it means it's a base. So what does that mean? Well, the acid is able to break apart in a solution or when it reacts to make a hydrogen ion. And we see in the formula of the three that we need to know this year, hydrochloric, sulfuric, and nitric, that they break apart into these ions. In every case, it makes a hydrogen ion. These hydrogen ions is what gives an acid its properties. It's why its pH is lower than 7, so it's a bit of a backward scale. The lower the number, the more hydrogen ions it provides. The higher the number, the more likely it is to grab hydrogen ions off things. So being less than 7, which is our middle mark for neutral, so water would be 7, means that it's got lots of hydrogen ions. Because of this, it will react with things like metals and carbonates and other things. It could do damage to us if the pH is low enough, so enough hydrogen ions. We can't actually tell how acidic something is until it reacts, because most acids are colorless. That means we have to have something to test how acidic it is or whether it's an acid or a base before we actually touch it, so that we know if it's dangerous or safe. The most simple way is to use a chemical called litmus. And we're going to use litmus paper in our experiment very shortly. In litmus paper, if you put litmus paper in it, it'll either stay red if it was red to start with, or it'll turn red if it was blue. So there's two types of litmus paper, blue and red. And the blue stuff, if it turns red, is telling you it's an acid. It doesn't tell us how acidic it is, just that it is an acid. The universal indicator, though, is a solution we use, and it's got a range of colours. All the colours of the rainbow, very conveniently. So, Roy, G, Biv. So, the red, orange, and yellow are our acids. Red is down here, then orange, then yellow, green is neutral, then blue, and then your purples are what we call very strong bases. So we can use universal indicator to go, how acidic or how basic is it? Now, that's how acids dissociate. Bases dissociate a slightly different way. They dissociate into ions. We've learned our table of ions, playing a bit of bingo. They dissociate into ions that can neutralize H+. So that's your hydroxides, your carbonates, and your hydrogen carbonates. So just putting an H at the front there. Their pHs are always above 7 because they can grab hydrogen off things. So up here, grabs hydrogen off things really easily, enough to grab it off you and to cause you chemical burns. So things with a pH up here are really, really bad for us to get on our skin. We wash them off straight away. Ideally, don't get them on us in the first place. Down here are things that we use. Ammonia as a cleaner. You should use gloves, but if you get it on you, it's not urgent to get it off you. Toothpaste is somewhere around here. It's a little bit alkaline, a little bit basic. Okay? So all of their pHs are above 7. If you had red litmus, it would turn it blue. If you had blue litmus, it would stay blue. And our universal indicator, as I say, purple through to blue. So our colours of the rainbow. When we join these things together, we've got our neutralization reaction. So this is called neutralization. So now I crouch down to write that. And a product of neutralization is always water. It always makes water. And that makes sense because water is probably our most common neutral substance. It also makes a salt. And we're going to spend a bit of time on this when we do the reactions of acids, so I'm not going to do much more detail there. But what we would find if our neutralization reaction worked perfectly, so there's no acid left and there's no base left, our blue litmus paper would stay blue. Our red litmus paper would stay red because it's not an acid or a base. And our universal indicator, hopefully as my color coding is trying to show, would be green. So what do we need to get out of this? Well, we've got our definition of acids already from earlier. We need to know that their pH is below 7. Even if it's as high as 6.9, it's still technically an acid. Because it's got hydrogen ions, its pH is less than 7. Because it's got hydrogen ions, it'll turn blue litmus red. Because it's got hydrogen ions, it will turn universal indicator anywhere between red and yellow on our rainbow spectrum, as it were. And the red end is very, very strong acid through to what we call a weak acid here. Bases are exactly the opposite. They have got a pH greater than 7. They turn litmus blue. So if it was red litmus, it would turn blue. And their colours are blue and purple if you're using the universal indicator. They don't have an ion that they release that we could say is the base ion. The anions or the negative ions they release neutralize H+. Any questions while I've still got that shit?